Hi guys, Nicole here from the Exam Revolution team, and in this aircraft technical and general video, we'll be discussing fuel systems. What we are going to cover, we'll have a look at the various fuel systems, then we'll have a look at fuel metering systems, fuel grades, fuel management, and lastly, fuel emergencies. Now let's get started with the various fuel systems. Now the function or the purpose of a fuel system is to store and deliver fuel to the engine in adequate quantities and at the correct pressure. Now in order for us to deliver fuel to the engine, it must be stored somewhere. So fuel is stored in the fuel tanks located in each wing of the aircraft, with the fuel system for a high wing and a low wing aircraft differing slightly, which will be discussed later on. This is just an example of what the fuel tanks would look like inside the wing, and you can see that each tank has a filler cap that obviously can be filled with fuel. Then from the fuel tanks you'll have two fuel lines going to a central point usually, and that goes to a fuel selector valve, and then from the fuel selector valve you have a single fuel line going to the carburetor, which supplies the engine with its fuel. Now the fuel tanks are vented to the atmosphere to prevent the flow of fuel from stopping and the tank from collapsing. So as fuel is drawn from the fuel tank, it must be replaced with air. So if you look on the right hand side of these fuel tanks, you can see the fuel tank vents, and it says the tank vent is designed to be non-siphoning and to vent clear of the airframe. So non-siphoning means that it's not drawing any fuel from the fuel tanks. Now tank venting allows air to move into and out of a fuel tank and equalize with the pressure outside the tank. If any tank is not properly vented, it can collapse or explode. So this is an example of a fuel tank that has not been, or a tank that has not been properly vented, or that has a blocked vent, and you can see the suction causes a collapse of the tank and also a stoppage in the flow of fuel. Now aircraft fuel tanks have a low area called a sump that is designed as a place for contaminants and water to settle. The sump is equipped with a drain valve, which is used to remove the impurities during a pre-flight walk-around inspection. So this is an example of a fuel tester, and remember that the fuel tank has a low point that has a drain attached to it. So when the fuel has settled, the fuel or the water and sediment or solid particles is heavier than fuel, so it will settle at the bottom of the tank and move to the lowest point of the tank, where you are able to drain and check for any impurities. Now a fuel strainer is also known as a gasculator, acts primarily as a fuel drain for water and small particles of sediment, and is usually found at the lowest point of the aircraft's fuel system. So the fuel strainer or gasculator is located below the level of the aircraft's carburetor and fuel tanks, and on light aircraft it is commonly located on the front of the firewall as low as possible. So this is an example of where a gasculator could be located. It's either on the lower left side of the aircraft fuselage, where there's an opening in the cowling, or it's directly beneath the engine, where there's an opening between the cowling and the aircraft, and then you can access a drain to drain the gasculator's contents. And this is typically what a gasculator could look like. In the top you can see a fuel intake, so where the fuel comes in, then it goes through a filter or a screen that removes the impurities like the water or any solid particles, and then you've got a fuel outlet once again. Right at the bottom of the fuel gasculator is somewhere that you can drain away the contaminants. So you can check if there are any water or sediment in the gasculator by just using your fuel tester once again. Now if contaminants like water or fine particles are found in the fuel, the normal procedure is to keep draining the fuel from the tank sump and the fuel strainer until the fuel is clear of any contaminants. If you cannot clear away the contaminants, you may not fly, and the aircraft will have to go in for maintenance. Now, in a high-wing aircraft, the fuel tanks will be higher than the engine, and the force of gravity is used to deliver the fuel from the tanks to the engine. This is referred to as a gravity-fed system. So this is an example of an aircraft with high wing and a gravity-fed system because the tanks are in the wings and obviously higher than the engine. So you can see fuel lines going from the tanks to the engine. Now, gravity-fed systems are designed and tested to make sure that they can supply 150% of the fuel flow required to operate the engine at maximum power at the least favorable attitude. The least favorable attitude being either a high nose climbing attitude or a steep banking angle. And the manufacturers have to make sure that more than enough fuel is being supplied to the engine to operate at maximum power at all times. Then the fuel lines transport the fuel from the wing tanks to a fuel selector valve. So this is an example of a gravity-fed system, and you can see on the very top is your fuel tanks, and then your fuel lines go from your fuel tanks to a fuel selector valve. The fuel selector valves allow you to use the fuel from the tank or from the selected tank, so that can either be used from the left tank, the right, or both, or to switch the fuel off and starve the engine of fuel in an emergency. So this is an example of what a fuel tank selector could look like. However, different aircraft have different designs. So this is typically what you would find in a Cessna 172, and you'd have both. If you have both selected, you would be drawing fuel from both fuel tanks. If you have left selected, you would only be using fuel from the left tank. And if you were using the right tank, or selected on the right tank, you would only be using fuel from that tank. Then your off position, in case of a fire, you can shut the fuel off and prevent it from getting to the engine. Now fuel moves then from the fuel selector to the fuel filter to remove any solid particles in the fuel. So this is typically what you might find in a fuel filter, and so its purpose is to remove any solid particles like sand or dirt or any sediment from the fuel before it gets to the engine. Then a fuel line is routed from the fuel filter to a fuel primer, and it is only used to help start the aircraft by injecting vaporized fuel directly into one or more of the engine cylinders. So if we have a look at our example again, you can see the fuel goes from the tanks via fuel lines to the fuel selector, then onto a fuel filter, and then you can see two fuel lines from the fuel filter, one going to the primer. And the primer is simply a little hand pump inside the cockpit, which you will unscrew and then you'll pull it back, and you can actually hear the suction of fuel. And if you push in, you can hear, or you won't be able to hear, but you can imagine that it's squirting fuel directly into the cylinder of the engine to help start. Once you have used the primer, you will then lock it back in place and start the engine, and thereafter it will stay locked. Then another line is routed to the carburetor, and the carburetor forms part of the engine induction system and is responsible for mixing the air and fuel. The mixture of fuel and air is then routed to each cylinder where it is burnt. So here you can see from the fuel filter, your other line or fuel line goes directly to the carburetor. So once the engine has started, the carburetor takes over and supplies the engine with its fuel. Now that was a high wing system or a gravity-fed system. The low wing is slightly different. So in a low wing aircraft, the fuel tanks are lower than the engine, and therefore a fuel pump is needed to deliver the fuel to the engine, referred to as a fuel pump system. So very similar to the gravity-fed system, except now that the tanks are lower than the engine, but we still have a fuel selector. Then the fuel goes through a fuel filter, and you can see one line goes to a primer and the other line goes first through the engine pumps, which obviously draws the fuel from the tanks, and then it goes on to the carburetor. Now an aircraft with a low wing usually has two fuel pumps, an engine powered fuel pump which operates automatically, and an electric fuel pump which is operated by the pilot from the cockpit, so in case of the engine driven pump failing. So if you have a look at this example again, you can see two fuel pumps, an electric pump and an engine-driven pump. And as mentioned, the engine-driven pump runs with the engine and is on automatically. And the electric pump will only be turned on in certain phases of flight or when the engine-driven pump has failed. Now the fuel pump, or it's also known as a boost pump, is normally fitted between the fuel filter and carburetor of a fuel or fuel control unit and should not be run when the system is dry. Fuel control unit refers to a fuel injection system, which we'll chat about later, but you should not run the electric fuel pump when the fuel system is dry. So having a look at that once again, you can see that the fuel pumps are located between the fuel filter and the carburetor. Now you also have something called an auxiliary fuel pump, which is exactly the same as an electric fuel pump or a boost pump. Auxiliary simply means a backup system. So some high-wing aircraft have an auxiliary fuel pump or boost pump installed to make sure that the fuel pressure is kept within limits, to get rid of any fuel vapor in the fuel lines, or to prime the cylinders in a fuel-injected system. Now let's have a look at a few exam examples. So our first question simply states fuel pumps. Now there can be a number of options, and obviously from the exam you would simply select the correct option. So fuel pumps is either a backup system to the engine-driven fuel pump, or it can aid in priming the engine, or it can help with keeping fuel within limits or removing vapor in the fuel lines. But the answer that they're looking for is that it should not be run when the fuel system is dry, and this is because fuel lubricates the fuel pump, and so if there's no fuel going through the pump while it is on, it could overheat or damage the fuel pump. The next question is, where in an aircraft engine fuel system is the electric fuel boost pump normally fitted? So where is the fuel pump located? And remember, that's located between the fuel filter and the carburetor. And the answer is between the fuel filters and the carburetor or the fuel management unit. Fuel management unit is with a fuel injection system. Now, an aircraft equipped with fuel pumps, when is the auxiliary electric driven pump used? Once again, we discussed a number of ways that the backup or the boost pump is used for or used in, and the answer that they're looking for is in the event the engine driven fuel pump fails. Then the next question simply states the primer is, and remember what a primer is for. It is simply used to start the engine by injecting vaporized fuel directly into the cylinders. So the answer is an auxiliary pump in the fuel system to facilitate engine starting. Next question is, what is the purpose of an auxiliary fuel boost pump installed in some light aircraft? Again, it should be to prime the engine or to supply fuel in case the engine-driven pump fails. And the answer is providing fuel to the carburetor during startup and supplying fuel if the engine-driven pump fails. Now, to properly purge water from the fuel system of an aircraft equipped with fuel tank sumps and a fuel strainer quick drain, it is necessary to drain fuel from. So the fuel strainer quick drain is simply the gasculator, and remember the lowest part of the fuel tank is called the sump tank drain. So you need to drain from both of those points if there are any contaminants found. So the answer is fuel strainer, drain, and the fuel tank sumps. Let's now have a look at fuel metering systems. Now, before fuel enters the cylinders to be burnt, it must be mixed with air in the correct ratio. So air in the mixture provides the oxygen needed to burn the fuel completely. So if the correct amount of air is mixed with fuel, the engine will develop maximum power for certain operating conditions. So this mixture that we talk about of fuel and air, fuel must be mixed with exactly the correct weight of air. So this ratio is normally 1 to 15. This means that in order for 1 kilogram of fuel to burn completely, we need 15 kilograms of air. So the purpose of these systems, or the fuel metering systems, is to sense the amount of air entering the engine and add the correct amount of fuel for that air. Now, there are two systems are used to mix the fuel and air before it enters the cylinders. They are the carburetor and the fuel injection system. Now, the carburetor system mixes the fuel and air in the carburetor before this mixture enters the intake manifold. So that's before it reaches the inlet valve of the engine. So if you have a look at this diagram, you can see that air is ducted in from the outside. It goes through an air filter. You can see the blue arrows there, and that gets then via piping goes into the carburetor of the aircraft. There are also red arrows, which is warm air from the carburetor heat, which we will discuss later, but we'll ignore that for now, and we concentrate on the outside air being ducted into the carburetor, where it's then mixed with air and then goes to the engine. Now, talking about the carburetor, it has something called a float chamber. So the liquid fuel is delivered from the wing tanks to the carburetor through a filter in the float chamber. So if we have a look at that, you can see that the carburetor is connected via a fuel line to the fuel tanks, and that fills up the float chamber. And before it goes to the float chamber though, it first goes through a fuel filter or fuel screen to make sure that there's no particles entering the carburetor, because there's very small tolerances in that carburetor. Then a needle valve is operated by a float, opens and closes to keep the fuel level constant. So as the fuel level drops inside the float chamber, the valve opens, allowing more fuel to enter. So if we have a look at the carburetor float chamber, it is quite small and so therefore can easily overflow. So connected to a float, the little green float in the float chamber, it's connected to a needle valve. So as the level of the fuel in the float chamber increases, that causes the float to rise and close the needle valve, and therefore stopping fuel from entering the float chamber. However, as the level drops in the float chamber, the float descends with the fuel level and therefore allows the needle valve to open and letting more fuel into the float chamber. Now, once the fuel is in the float chamber, it goes then to something called a metering jet. So the fuel moves from the float chamber to the metering jet, and the metering jet is simply a small opening that limits the rate of fuel flow. So as you can see on the right hand side, there's a small little opening that limits the amount of fuel going to the engine. Now, if there was no metering jet, it will result in a very high fuel flow rate, which means that the engine would receive too much fuel and could flood the engine. But how is the fuel and air mixed inside the carburetor? So the air enters the carburetor from the outside, from the front of the engine cowling, through an air filter called the air intake. So if you have a look on the left hand side, you can see the nose of the aircraft has an air intake there with a air filter. And if we look at the picture in the middle, you can see from the air intake, the air is ducted through lots of piping through to the carburetor. Now this filtered air then flows through a venturi built into the carburetor, and as air flows through the venturi, a low pressure area is created and fuel is sucked through the discharge nozzle that vaporizes the fuel. So if you look at the bottom of the carburetor, on the right hand side, you can see the fuel entering from the the air entering from the outside, and then it goes through the venturi. So as you move up the carburetor, you can see that the throat of the carburetor narrows. That narrowing or decrease in area is called a venturi and creates a low pressure area. Now the discharge nozzle is located in the throat of the carburetor where the pressure is lowest, and the difference in pressure will force fuel to move from the float chamber through the metering jet and through the discharge nozzle. So now we have a low pressure in the throat of the carburetor in the venturi, and then you've got a high pressure in the float chamber region. And so this difference in pressure causes the fuel to flow from the high pressure area to the low pressure area, and therefore it's pulled through the discharge nozzle, and this is where it's mixed with the outside air going to the engine. The discharge nozzle is a very special nozzle that vaporizes the fuel or atomizes it and mixes it with the air. Now, the greater the airflow into the engine, the faster the air must flow through the venturi and the lower the pressure will be. So this means that it just increases the rate of fuel, and therefore with the faster your engine is moving, it needs more fuel and air, and because of this increased airflow, it will increase the fuel as well. Now, the ratio of fuel to air of the mixture is controlled by the throttle and the mixture control levers that are situated in the cockpit. So again, all aircraft have different designs. This is a typical design of your throttle. You can see it in the black lever, and your mixture on the right hand side. Now, the throttle valve operates the butterfly valve situated in the venturi of the carburetor, and as the throttle is opened, the valve opens, which allows a greater volume of air to fuel to enter the cylinders. So in the throat, on the top of the throat of the carburetor, you can see a butterfly valve, and your throttle is connected to that butterfly valve. So in opening the throttle will open that valve, closing the throttle will close that valve, and you can see that it will allow a certain amount of fuel and air to go to the intake manifold and therefore go to the engine. Now, in an aircraft with a fixed pitch propeller, opening the throttle results in an increase in RPM and therefore an increase in thrust, and vice versa. So as we gain altitude though, the air becomes less dense. This means that we do not have as much air molecules to mix with the fuel as we did at lower altitudes. The mixture can be used to decrease the amount of fuel mixed with the air as we gain altitude. So pushing the mixture lever forward allows more fuel to enter the discharge nozzle in the carburetor venturi, increasing the ratio of fuel to air. This is called enriching the mixture. So here's an example of a mixture that is connected to the needle valve inside the float chamber. And you can see that pushing it all the way forward means that that valve or needle is at its highest point, so it allows the maximum amount of fuel to mix with the air going to the engine. So on the left hand side you can see that for that type of mixture lever, you push it in and push it all the way forward, and this is a rich mixture. Pulling the mixture lever backwards allows less fuel to enter the venturi, decreasing or leaning the mixture. So now if we look at our flow chamber, you can see that that needle valve is much lower, decreasing the amount of fuel going to the discharge nozzle. And in this example, this type of mixture lever, you can simply turn it to fine tune decreasing the mixture, or you can simply pull it out as well. Then pulling the mixture lever all the way back results in no fuel being discharged to the venturi. So with no fuel entering the engine stops and the mixture is said to be at idle cutoff. So having a look at our example again, you can see that this needle valve completely shuts off the fuel from the float chamber, and therefore no fuel is going to the engine and will shut the fuel off. At low power settings though, the force created by the difference in pressure might not be enough to supply enough fuel to the engine. This problem is solved by installing an air bleed. Now an air bleed, so air that is close to or at atmospheric pressure, which is high pressure, is fed into the diffuser nozzle, and air is then mixed with the fuel before it leaves the diffuser, and this provides a more constant fuel-air mixture as the airflow changes. So you can see on the left hand side there we have an example of an air bleed, and that's got a little line that connects directly to the discharge nozzle. So before the fuel exits the discharge nozzle, that air is mixed into that fuel stream, and this helps to keep the engine going at lower power settings. Now the air drawn into the diffuser nozzle from the air bleed also helps to vaporize the fuel and provide a more even fuel discharge through the full range of power settings. So when the engine is idling though, the butterfly valve is closed, creating a higher pressure ahead of the valve and a low pressure behind the valve. So once again, in your float chamber, you've got a high pressure, and closing the throttle will close that butterfly valve, and so therefore you have a low pressure ahead of the valve and a higher pressure behind that closed butterfly valve. And this will then cause the fuel to flow through a different route bypassing the throttle valve to help idle the engine. So the idle passage allows fuel to come directly from the float chamber to the low pressure side of the butterfly valve. So if you have a look at that image again, you can see that the idle passage bypasses the butterfly valve and allows the engine to have a supply of fuel to run the engine during idle. Now when the throttle is open though, the pressure difference is large enough to allow fuel to be drawn through the diffuser nozzle once again. Then you also have something called an accelerator pump. So the accelerator pump squirts a stream of extra fuel into the intake air as the throttle is advanced. So the sudden burst of extra intake air creates a lean condition and causes the engine to stumble, especially if the throttle is opened suddenly. So the throttle accelerator pump prevents that by squirting an extra bit of fuel into the stream, and therefore the engine operates smoothly when you suddenly increase the power. So that's an example of the accelerator pump in the float chamber. It just simply consists of a plunger or a piston that immediately gives a squirt of extra fuel to help with the running of the engine when you advance the throttle very fast. Now the carburetor is not without its problems. The main issues associated with the carburetor is icing. Now carb icing, or icing inside and around the carburetor, is usually referred to as carburetor icing, and it affects the fuel-air mixture going into the engine. It can even potentially starve the engine of fuel and air, causing an engine failure. Now there are three types of carburetor icing that can occur. They are impact icing, fuel ice, and throttle ice. And this type of icing is most common when flying in visible moisture such as clouds, snow, sleet, or rain. So that's impact icing. So remember, you've got an air intake, and that's the only source or one of the only sources of air in front of the aircraft engine, supplying the engine with air. And so when flying in clouds, so water droplets within a cloud can stay in its liquid form well below 0 degrees Celsius. But when the droplets come into contact with a solid surface, it freezes on impact. So if you have a look at this diagram, you can see the different temperatures. So if the temperature is below 0 degrees Celsius, there's no threat of icing really. But the minute the temperature drops below 0 degrees Celsius, supercooled water droplets can stay in its liquid form, and therefore once the aircraft flies through it, it can freeze on impact. And you can see above -40, you don't have any threat of icing because all of those water droplets has already frozen. So impact icing can affect or block the air intake and the air filter or the fuel nozzles inside the carburetor. So if you have a look at this image over here, you can see how on the right hand side the fuel as it impacts the air filter and around in the induction piping and filtering, you can see that the ice has started to form, and that also can prevent the air from getting to the engine. Then fuel ice. So when fuel is introduced into the carburetor, the fuel is vaporized. This vaporization causes the fuel air mixture to cool down below dew point temperature, and the moisture in the air will condense and freeze. So fuel ice can occur when the outside air temperature is between 20 to 30 degrees Celsius with 50% humidity or higher. So you do not need to fly through cloud or visible moisture for this type of icing to occur. So throttle ice then is the last type of carburetor icing. So as air moves through the carburetor's venturi, the pressure decreases, expands and decreases in temperature, and if the throttle is partially closed, the mixture can be restricted or prevented from going to the engine. So if we have a look at this example, the throttle icing impacts around the throttle butterfly valve and also around the valve itself, and being severe enough, it can cut off the entire fuel-air mixture to the engine. Now, throttle icing most often occurs during a descent at low power settings. Now, the signs that may indicate carburetor icing is a drop in RPM, a rough running engine, or even an engine failure. So carburetor icing is most dangerous within a temperature range of -10 degrees to +25 degrees Celsius in cloud, fog, or precipitation at any power setting, but most likely to occur at 15 degrees Celsius in the early morning with visible moisture in the form of mist or fog. So if you have a look at this graph, you can see the temperature on the horizontal or the bottom of the graph. You can see that it's going from -20 to +40 degrees. Then the vertical scale, or the scale on the right hand side, indicates dew point temperature, and you can see that the relative humidity as the lines going diagonally across the graph, and you can see that 100% humidity with the temperature being at 10 degrees and the dew point being very close to that as well, or the same 10 degrees. You can see that you have a possibility of severe icing at any power setting. Then the further you move away as the temperature increases, the severity of the icing lessens. However, within the carburetor itself, you can fly at warm temperatures and still have cold or temperatures below freezing level inside the carburetor, which increases your risk of icing. Now, carburetor icing is corrected or fixed by applying carb heat. So carb heat directs hot air into the carburetor and melts the ice. Carb heat is an alternate source of air if the air intake is also blocked. So how does the carb heat work? Well, a shroud is fitted around the exhaust, which heats up the air in contact contained within the shroud. A lever situated in the cockpit opens a valve, which allows warm air to enter the carburetor. So you usually have a small little lever inside the cockpit called carb heat, and you usually will pull that all the way out. And what happens is, you can see at the bottom where your usual air intake happens, you can see the blue arrows, and you can see that on the main picture that is blocked. So the carburetor heat valve is open in the cockpit and it's not allowing outside air to enter the engine. So if you look to the right, you can see that if the carburetor heat valve is closed, the cold air is now getting into the engine. So when the valve is open, if you look on the top of the propeller, you can see the outside air coming in, and that air is ducted to air that's within an exhaust muffler or in a shroud, and that air is heated up just being in contact with the exhaust, and then once you open the valve, it allows that hot air to go into the carburetor and hopefully melting the ice that is in the carburetor. Now, hot air is less dense, and therefore the mixture will richen if nothing is done to the mixture setting, and decreases the power by 10% to 20% because of that hot and less dense air. Now, the air being used from the carburetor heat system is unfiltered, and therefore caution must be used when using carburetor heat on the ground, as sand or other solid particles can be fed into the engine. So when carb heat is applied, if ice is not present, you will see a slight drop in the RPM. If ice is present, a rough running engine and a large RPM drop will be experienced, followed by an increase in RPM as the ice melts. So it obviously will get worse as the engine ingests the melted water before it gets better. Now let's have a look at fuel injected systems. So in a fuel injected system, the fuel is injected directly into the cylinders and consists of the following components: an engine driven fuel pump, a fuel air control unit, a fuel manifold, a discharge nozzle or discharge nozzles, an auxiliary fuel pump, and fuel pressure and fuel flow gauges. So this is an example of a fuel injected system. So from the fuel tanks, you have fuel lines going to your engine-driven or an auxiliary fuel pumps, and then onto a fuel air control unit. And from that unit, it goes to a fuel manifold or a fuel distributor, and that distributes to the various engines. You can see lines going from the fuel distributor to each cylinder which injects the fuel directly into the cylinder. Now the auxiliary fuel pump provides fuel under pressure to the fuel air control unit for engine starting or for emergency use. So after starting, the engine driven fuel pump supplies the fuel pressure required. Now the fuel control unit measures a certain amount of fuel based on the mixture setting set by the pilot. The metered fuel then flows to the fuel distributor or the fuel manifold. So as mentioned there, you can see on the right hand side your throttle and mixture levers, and you can see if you go to the left, you can see it is connected to the fuel control unit and also to the throttle body where it controls the amount of air going to that fuel distributor as well. Then you can see your electric fuel pump below your mixture and throttle controls that goes through the mechanical pump and once again goes through the fuel control unit, and that then flows into the fuel distributor, which then distributes the fuel and air. Now the fuel is then distributed from the fuel distributor to separate fuel lines, which carries the fuel to discharge nozzles in each cylinder head. So once again, you can see the fuel distributor looks kind of like a spider on top of the engine, and it has fuel lines going from that distributor to each cylinder, and each cylinder has a fuel injector that then sprays your fuel and air mixture directly into the cylinder. Now outside air is ducted through a venturi, and the throttle controls the amount of incoming air transported to the cylinders in the same way as a carburetor system. So that throttle will open or close a valve which also controls the amount of air going into the cylinders as well. Now if the air intake becomes blocked, an alternate air source is available and opens automatically if a blockage does occur. Usually there is a control in the cockpit if the alternate source does not open automatically. So if your air intake becomes blocked because of icing, there is an alternate air source, which is sort of just a flap. And once again, this is unfiltered air. Now a common problem with fuel injection systems is vapor lock. Now vapor lock happens when fuel in your fuel lines vaporizes. It turns from liquid to a gas. The vapor lock is most likely to occur in fuel injected engines. So what happens? So when your fuel lines are full of vaporized 100 low lead avgas or aviation gasoline, your fuel pump can't get liquid fuel to the injector nozzles, which makes starting your aircraft frustrating, difficult, or impossible. So why does it happen? Well, vapor lock is most likely to occur in fuel injector lines after the fuel flow divider. So as fuel is sent to the injector nozzles, this is because the heat from the engine cylinders and crankcase radiates outwards up towards the fuel injector lines. So those are the lines after the fuel distributor, and that after you shut down gets heat radiated from the engine and turns that liquid fuel into gas. So if you have a look at this example again, you can see that after the fuel distributor, each line, because of the heat coming from that crankcase and cylinders going to each cylinder, has vaporized fuel in it. Now vapor lock typically starts when you shut down an engine, and as you shut down, the heat rises upward toward the fuel lines. Without air moving through the cowling, fuel in the lines can start to vaporize. Now the only real solution is to push the air bubbles out of the lines is by pumping fuel through the lines with a boost pump or a fuel pump. Let's now have a look at some exam examples. Applying carburetor heat will. Again, there can be a number of options. Remember that carburetor heat decreases the performance of your engine because it's less dense air, but carburetor heat is used to melt the ice if there is any present in your carburetor. And the answer that they're looking for is to enrich the fuel-air mixture, and this will enrich the fuel-air mixture because the air going into your engine now is less dense, and with the same amount of fuel, it now becomes richer. It's too much fuel for the air. Then the next question is, generally speaking, the use of carburetor heat tends to, and this answer should be to decrease your engine power. So the answer is decrease engine performance. Then the next question is, the presence of carburetor ice in an aircraft equipped with a fixed pitch propeller can be verified by applying carburetor heat and noting. So you should see a decrease, a large decrease in the RPM, have a rough running engine, and then after a while, once it gets better, the RPM should increase. The answer they're looking for is a decrease in RPM and then a gradual increase in the RPM. Which condition is most favorable to the development of carburetor icing? So your conditions are normally about 15 degrees Celsius outside with a very high humidity. But obviously carburetor icing can happen at any power setting and can happen on quite a hot day, just depending on the amount of moisture in the air at the time. The answer that they're looking for is the temperature being between 20 and 7 degrees Fahrenheit. So that's -6 to -21 degrees Celsius with a high humidity. Then vapor locks in a fuel system pipelines are prevented by the boost pump. We just discussed it. The only way to get rid of the air bubbles or the gas fuel in the lines is to pump liquid fuel through the lines to help start the aircraft. Then where in an aircraft engine fuel system is the electric fuel boost pump normally fitted? This will be very similar to the carburetor, and it's usually between the filter and the carburetor or the fuel distributor. Let's now have a look at your various fuel grades. Now, piston engine aircraft use gasoline fuels called aviation gasoline or avgas. So by looking at this table, you can see on the left hand side you have all the grades that are used normally for light aircraft. You have avgas or aviation gasoline 100 LL, which stands for low lead. You've got avgas 100 and then avgas 115. Then the performance number, so you've got 100 to 130, both for avgas 100 LL and for 100, and then 115 to 145. So these are the octane ratings for your engine that can use this type of fuel. And then with aviation gasoline, it's normally identified by a color. So for 100 LL or low lead, it's a blue in color. And for just avgas 100, it's green in color. And then the specific gravity of the fuel, which you can do calculations to work out, calculate the weight of the fuel. And then your lead content is either low lead or high lead. Now, the lead content is important in terms of the octane rating, which we'll chat about in the next few slides, but a high lead content when burnt is quite a bad pollutant to the atmosphere, so therefore using low lead is better for the atmosphere. So as mentioned, we use normally avgas with 100 octane, 100 either blue or green in color for our light aircraft. Now, the fuel or the octane rating of the fuel is specified with the grade. So for example, avgas 100 is 100 octane fuel. And octane rating simply indicates the amount of fuel or that can be compressed before it spontaneously ignites. So we want quite a high compression because that means more power, and so therefore you want a higher fuel with a higher octane rating so you can get more power from your engine. So a higher octane rating is more stable and produces better efficiency and power, while a lower octane fuel will handle less compression before igniting. So remember that piston compresses the fuel air mixture, and so if it's a low octane rating, it will ignite before the spark plug goes off, which is not a good situation. So what is anti-knock? Octane in fuel gives an indication of anti-knock or anti-detonation value, which is an indication of the compression that the fuel can withstand. So again, anti-knock has to do with pre-ignition or detonation, where the fuel ignites before it's supposed to. Now, knocking happens when the fuel in the cylinder ignites before it should, and this premature ignition disrupts the smooth rotation of the engine, by firing before the piston reaches the top of the cylinder. So never use a fuel of a lower octane rating or expired fuel. If using fuel of a higher octane rating, spark plugs could become fouled because of the excess carbon buildup, and the exhaust valves can become eroded. So if you can't get the correct octane of fuel, never use a lower octane, rather use a higher octane. However, higher octane can cause spark plug fouling. Let's have a look at a few exam examples now. So what does the octane rating or fuel grade describe? So remember, this is the amount of compression that the engine can compress the fuel to before it ignites. So the answer that they're looking for is the anti-knock rating. So you don't want the fuel to ignite before the piston reaches top dead center, and so therefore if you have a low octane, it will ignite before the piston reaches its proper top dead center position. The cylinder head and the oil temperatures may exceed their normal operating ranges if, let's have a look at what they're looking for. The answer is a lower octane rating than specified for the engine is used. So if you have a low octane, your cylinder head temperatures and your oil temperatures will be higher than normal. Let's now have a look at fuel management. Now, most aircraft have fuel gauges installed, which is either electrical or direct reading. Now, fuel quantity gauges are more accurate when the tanks are full, but accuracy decreases as the fuel is used or decreases, and when it's turbulent conditions. So this is an example. Again, each aircraft has a different design, but this is an example of a fuel quantity gauge for the left and right tank. And you can see that the top top markings there indicate the capacity of each tank, and the lower or the red line indicates the unusable fuel in the tank. So the best method is to always check fuel visually or with a dipstick if possible. So fuel planning for the expected fuel usage is extremely important due to these inaccuracies. So here's an example of dipping a tank, which is much more accurate, and then you can compare this to the readings on your fuel gauges to make sure that they are accurate as well. Then your fuel pressure gauge can give you an indication of trouble before takeoff. It tells if the auxiliary pump is working, so that means that if the engine is off and you put your auxiliary pump on, the fuel pressure should rise on your gauge. It can also tell you whether the engine-driven pump is working, so that means your engine is running, but your electric or your boost pump is off and the engine is still running. That means your engine-driven pump is operating fine. And it can tell you whether there is vapor in the fuel lines. Now this is an example of a fuel pressure in PSI, and obviously the green range is where you want the fuel pressure to be throughout the operation of the aircraft. Now, a fuel flow meter indicates an engine's fuel use in real time, and this can be useful to the pilot for ascertaining engine performance and for flight planning calculations. Now, not all aircraft are fitted with a fuel flow meter, so you can see that it will tell you how much fuel you're currently burning at a particular power setting in gallons per hour. Then when refueling your aircraft, it's very important to follow certain steps. So one of the first steps you do would be to attach the grounding wire to a bare metal part of the aircraft, and this will prevent sparks due to static electricity. So remember, when attaching the grounding wire, you can attach it to bare metal like the exhaust. However, you need to take caution when the exhaust is hot. Then when filling the tanks, and visually confirm the fuel level. So always make sure that you look inside the tank to visually confirm that fuel level. Certain pilots operating handbooks will tell you at a certain point, like there's a step inside your tank that will tell you the level of the fuel at that point. Otherwise, visually check that you have, or the refueler has filled up the tanks to the top. So make sure that you visually check that fuel level inside the actual tank. Then double check the fuel caps to ensure that they're properly positioned and secured closed, especially if another person has refueled the aircraft for you. Always double check that they have been closed properly or have been closed or put on. It has happened that fuel caps have come off in flight. So once again, secure the fuel caps. Then wait for the fuel to settle if you have time before draining the tanks, and if any water is present, it allows the water to settle at the bottom of the tank. So if you allow the fuel to stand for 10 to 20 minutes, the water should settle in the lowest part of the tank, which you can drain and see if there was any contaminants in that fuel. Do not refuel while smoking or near an open flame. Then if you have a look at managing the fuel while flying, fuel tank selection is very important. So it's the pilot's responsibility to make sure that he or she selects the correct tank and manages the fuel correctly. If you have a design where you're either choosing a left or right tank, you have to make sure that periodically you change the fuel tanks to prevent imbalance or running one tank dry. When switching tanks, use the auxiliary fuel pump. So you'll switch it on, make sure the fuel pressure is within limits, change the tanks and make sure that the fuel pressure has stayed within limits before putting the boost pump off. Then if you forget to change the tanks and run out of fuel, do the following. Close the throttle to avoid surges, set the mixture to full rich and turn the electric fuel pump on and check and change the fuel selection if required. Now, fuel pumps should not be run when you have a complete fuel starvation, as it can result in the pump overheating, your auxiliary fuel pump. Let's now have a look at a few exam examples. What is the most reliable practical method of checking the fuel level in the reservoirs of an aircraft while on the ground? So we said the most reliable is visually checking the fuel, and that's either by looking inside the tanks that it's full or using a dipstick and then comparing it to your fuel gauges. So the answer that they're looking for is visually checking the fuel level in the reservoir or the tank. Then the next question is, what has to be considered during refueling? So we just discussed all of those points, is to make sure that the aircraft has a static ground, so there's no sparks, and also very importantly not to smoke or to refuel near an open fire. So I think fueling and fire is the most important aspect when refueling your aircraft. So the answer they're looking for is no open fires, obey the smoking ban and apply grounding cables. Then the next question is simply fuel pumps. So it can be what is their purpose, and we discussed this at length in the previous chapter. So the answer here is should not be run when the fuel system is dry. Remember that the fuel pump is lubricated by the fuel, so therefore if it's run dry it could overheat. Let's now have a look at some fuel emergencies. Now, during start, the most common cause of an engine fire during start is due to overpriming the engine. So what happens when you overprime during start? So for the engine to start, you need the correct fuel-air ratio, which is 15 parts air and 1 part fuel. If you prime too much, you have too much fuel for the amount of air in the cylinder, and the vaporized fuel becomes liquid again, and the fuel won't ignite. So now you've got this liquid fuel that won't ignite inside the cylinders, and remember, in a horizontally opposed engine, your cylinders are horizontal, so this can allow the fuel to collect in the induction chambers in the carburetor, so therefore this fuel will then run with regards to gravity into parts of the engine that it's not supposed to be. So this excess fuel can drop onto hot components of the engine, or a spark as you're trying to start the engine can ignite the fuel vapor, and this can result in a fire. Now, most manufacturers will publish the emergency procedures for extinguishing an engine fire during start in the pilot's operating handbook, so you must follow your exact aircraft procedure. This is just a generic procedure that you might find 8 out of 10 times in a pilot's operating handbook. And the first step is always to continue cranking. So the first procedure would normally be to continue cranking, and this means that you have to hold the key in the start position. When the pistons are moving back and forth in the cylinders, they are creating a suction that will draw the flames into the cylinders. So the starter turns over the engine, and this creates the suction that we require. So once again, keeping this key in the start position while you are doing all your other checks to make sure that you extinguish the fire. Then while you're still cranking, you move the mixture to idle cutoff position and put the fuel pump off and cut off the fuel supply. So remember that a fire needs fuel, air and spark, and so by removing one of those elements you can hopefully extinguish the fire. Then open the throttle. That helps to increase airflow and get rid of the excess fuel. And if the engine does start, it's normally recommended that you continue to run the engine for 1 to 2 minutes and then to shut down and inspect for damage if the fire is extinguished. If it does not start and the fire cannot be extinguished, while you continue to crank, set the fuel selector to the off position, set ignition switch to off, master switch off, take the fire extinguisher if there's time, and evacuate the aircraft. Then use the fire extinguisher where possible to extinguish the fire. So just looking at that example again, you can see on the left hand side it says danger signs. So you either might see flames or smoke coming from the engine, and you immediately want to try and extinguish that fire. So you're going to try and continue cranking and hopefully start the engine and suck the flames into the engine. If the engine does not start, if you look at number 4, then you're going to have to continue cranking. And while you're cranking, you're going to have to cut the mixture, so cut off the fuel supply by turning the fuel selector off. And once you've done that, you can turn the ignition off, masters off, and if you have time, grab the fire extinguisher and do what you can with that fire extinguisher. Let's now have a look at a few exam examples. Now, after starting a piston engine aircraft, you notice large flames developing from the engine. Your immediate actions should be. So in this question, they want to stop one of the elements of the fire, and that's going to be fuel. And so in this question, they say, shut off the fuel. So they answer, shut off the fuel feed immediately. Then in the event of an engine fire, again, it's asking about the procedures, and the questions can be quite different. So select from the options you have available to you. And the answer that they're looking for is the fuel supply is isolated from the engine by pilot action. So that's you pulling the mixture to idle cutoff and turning the fuel selector to the off position. Now that's all for this video. Thank you for watching, and see you in the next one.